Hi all. In this lab, we'll be exploring the biggest square in a rectangle problem. We'll first go through the problem statement and make sure we understand the problem by going through an example. We'll then take a look at a greedy algorithm to solve this particular problem. We'll then take a look at how the algorithm works on several examples and consider how we can make the algorithm more efficient. We'll then see that the algorithm in this lab is actually an important algorithm in mathematics that is over 2,000 years old. Finally, we'll use the algorithm in a mathematics application that expresses rational numbers in irreducible form. It should be fun. Let's get started. So here's the problem that we're going to solve in this lab. If we are given a rectangle with integer dimensions, our goal is to find the biggest square that fits exactly into the rectangle. Let's take a look at an example to see what this means. Here we have a rectangle that has a height of 8 units and a width of 20 units. Each unit is shown as a gray square. Now we could, of course, fill the rectangle entirely with 8 times 20 or 160 squares of side 1. This means that a square of side 1 fits exactly into the rectangle. But is this the biggest square that fits exactly? It isn't. For example, here we see that we could fill the rectangle entirely with 4 times 10 or 40 squares of side 2. So a square of side 2 also fits exactly into the rectangle. But again, is this the biggest square that does so? We might try to fill the rectangle with squares of side 3, but if we do so, we run into a problem. It is impossible to fill the rectangle completely. In this slide, we have 2 times 6 or 12 squares of side 3 placed in the rectangle, but part of the rectangle remains and it is impossible to squeeze in any more 3 by 3 squares. So a square of side 3 does not fit exactly into the rectangle. However, we see that we can fill the rectangle entirely with 2 times 5 or 10 squares of side 4. So a square of side 4 does fit exactly into the rectangle and is the biggest square that does so that we have seen so far. Here we have tried to fill the rectangle with squares of side 5. And just as in the case of squares of side 3, we have failed to fill the rectangle completely. So a square of side 5 does not fit exactly into this rectangle. We'll stop there, but we could continue trying to fill the rectangle with squares of different side lengths. If we do so, we find that the biggest square that fits exactly into this rectangle is the square of side 4 we saw in the previous slide. However, going through all the different possible sides of a square is inefficient, especially if we are working with large rectangles, say rectangles with sides in the millions. Let's take a look at a greedy algorithm that solves this problem more efficiently. The way this algorithm works is, given a rectangle, we take the largest side square possible from the rectangle. If, after removing the square, the rectangle has been completely removed, then it means that the square we have just removed is the largest square that fits perfectly into the rectangle. Otherwise, we are left with a new rectangle after the square has been removed, and we repeat the process on the new rectangle. This is an example of a greedy algorithm. In the lab, you are tasked with doing some research on greedy algorithms, so I won't say any more about them here, but let's make sure we understand how this algorithm works on a few examples of rectangles. Let's return to the example of an 8 by 20 rectangle. Here is a picture of the rectangle with the unit squares that comprise the rectangle shown in green. The first step is to be greedy and take the biggest possible square, which is the 8 by 8 square shown in red here, from the rectangle. After we have removed the square, we are left with a new rectangle shown in green here. Again, we take the largest possible square, again the 8 by 8 square shown in red, from the rectangle. And again, we are left with a new rectangle shown in green. This time, the biggest square we can take is the 4 by 4 square shown in red, so let's take it. And again, we are left with a new rectangle shown in green. The biggest square we can take now is the 4x4 square shown in red, so we take it. And finally, we have completely removed the original rectangle. This means that the biggest square that perfectly fits into the rectangle is the last square that we took, namely the 4x4 square, and we're done. Let's take a look at another example. What is the biggest square that can fit exactly into a 24x39 rectangle? Why don't you pause the video now, draw the rectangle on a piece of paper, and carry out the algorithm manually to make sure you understand the steps. Hit play again when you've identified the biggest square that fits exactly into this rectangle and you're ready to check your answer. Alright, here's the rectangle. The biggest square we can take is shown in red here, so we take it. And we're left with the green rectangle shown here. The biggest square we can take is shown in red, so we take it. And we're left with the green rectangle shown here. Here's the biggest square shown in red, so we take it. And we're left with this green rectangle. Here's the biggest square, so we take it. And here's the rectangle we're left with. Here's the biggest square we can take shown in red, we take it. And we're left with this little rectangle in green. Here's the biggest square we can take, which is a 3x3 square, so we take it. And we finally removed the entire original rectangle. Thus, the biggest square that fits exactly into the 24x39 rectangle is the square of side 3, and we're done. Is that what you got when you tried it yourself? Alright, I think you understand the algorithm at this stage, but let's take a look at one last example. For the final example, let's find the biggest square that fits exactly into the 25x46 rectangle. Again, pause the video now, work through the algorithm manually, and then hit play again when you're ready to check your answer. Okay, here is the rectangle shown in green. This time, let's just quickly go through the steps. In this case, the largest square that fits perfectly into the rectangle is the unit square. Is that what you got when you tried it yourself? What do you think this tells us about the height and the width of the original rectangle? Okay, so we have a pretty efficient algorithm, but I think we can improve it even further. For example, think about how the algorithm we have been discussing would work on a rectangle with a height of 3 and a width of 1,000,000. It turns out that the biggest square that fits exactly into this rectangle is the unit square. But how many steps would the algorithm take to reach this answer? Well, it would remove the square of side 3 333,333 times to leave a rectangle of height 3 and width 1, and then would remove a square of side 1 3 times before it would finally be done. That's a lot of steps. It turns out, however, that we don't need to repeatedly remove a square of a given side from the rectangle, but can instead jump directly to the rectangle that would remain after we have repeatedly done so. Can you see how? A hint lies in the word remaining. See if you can update the algorithm to improve its efficiency. At this stage, you should be able to complete task 4 of the lab, which is to implement the biggest square in a rectangle algorithm, and task 5, which is to test the algorithm on a set of given rectangles. Alright, in task 6 of the lab, you are asked to research a famous algorithm called the Euclidean greatest common divisor algorithm, which is over 2,000 years old. Although this algorithm is often not presented geometrically, that is in terms of rectangles and squares, you should find that it's equivalent to the algorithm we have explored in this lab. Enjoy finding out more about this algorithm, I won't say any more about it here. Great. Finally, in task 7, you are to use the algorithm in an application. You are to write a program that asks the user to input a rational number and then outputs the rational number in irreducible form. Let's take a look at what that program might look like at runtime. Here, the program prompts the user to input a rational number. Let's input 5/15. And the program gives us the result 1/3. In other words, 5/15 is equal to 1/3, but 1/3 cannot be reduced any further. In our minds, we should picture a 5×15 rectangle, but then instead of expressing the dimensions in terms of the unit square, we express it in terms of the largest square that fits exactly into the rectangle. Next, let's input 15/5. And our result is 3, though 3/1 would also be acceptable. Let's try 24/27. And we get 8/9. Let's try 27/24. And we get 9/8. Good. What about if we input a rational number that is already in irreducible form, say 1/5? In that case, the program gives us the same expression we input. Nice. So your task is to write a program that similarly takes in a rational number from the user and outputs the same rational number in irreducible form. And that's that. I hope you enjoyed the lab and are ready to write up the report. Have fun.